the calculus kid, Jerry!
Hello, my name is Jerry Gutierrez and welcome to Calculus in the AP level. Today we're going to be talking about the area in between two curves. Now before I get into it, I would like to just show you a quick example. This one right here, y equals negative x squared. From what you guys know, finding the area of this requires getting the function and then finding all of the area in between the interval all the way up until the x-axis, right? And the integral would look like the integrand from your limits. I always forget if it's b or a, but I think it's like that. Of the function in respects to x, right? The thing about this is that technically you guys are always doing something like this. Something like this, but let me explain something. What this f of x means is the top curve. And what I mean by the top curve, that's relative to the x-axis. What you guys are always doing is getting the top curve, which is f of x, and subtracting it from the bottom curve, which is bounded by the x-axis, g of x. But since the x-axis, it's 0 all the time, it'll just be minus 0, which just gets you f of x dx. But when finding the area in between two curves, this becomes really prime. You are really going to need the integral of the top function minus the bottom function. And throughout this video, I'm going to be yelling this at you because you really need to know this in order to understand the area between two curves. So let's look at our next example. Here we have this function here, let's call that f. And we have this function right here, let's call that g. So if you were trying to find the area between from a to b of g, it would be everything under g, which is what's in blue. Now let's move on to the next one.
No, I don't think so.
Let's try to find the area under the curve from a to b of f. As you can see, you have to include the area of g plus this guy. So the area of f contains g plus more. And if you want this part, which is the area between the two curves, g and f, what you would have to do is get the area of the top curve and subtract it from here. Getting rid of it, giving you the area in between two curves. So that's the main point I want to get across. Top curve subtracted by bottom curve. Let me just erase this. So let's do an example. Here I have two functions. Usually you'll find these problems like literally they just give this is a y. Literally they just give you two functions and then they just say find the area between the two curves. How you would go about this is first you want to draw your graph, 1 to see what you're looking at and 2 to see which curve is on top. We all know that x squared looks like this. And we all know that square root of x is almost the opposite, right? And we're trying to find the area between the two curves, which is this and that. So the area of r. So let's call it the area of r. And since we don't have anything that we know right now, let's try to write our integral. It's the area in between the top curve, which we said was x squared, or square root of x, I'm sorry, subtracted from the area of the bottom curve, which we said was x squared in respects to x, right? But there's one thing missing from this integral, and that would be the limits of integration. So how do we go about getting the limits of integration? If you want this, all of this area, you know that you're going to have to start here, whatever this is, and start here, whatever this is. Luckily there's a way we can do that. We have to find these intersection points right here in order to find our limits, and that's pretty simple. To find that, we just plug in. We don't plug in, we set the two functions equal to each other. And whatever we get should be our limits of integration. So let's just do some, I don't know what, algebra I guess, just to get our answer. Oops. And then to factor out an x. And then let's use this property that we all know. So we already know that one of the x is 0. So it's going to be to 0 to whatever this guy is. So we're going to have x cubed is equal to 1, and then cube both sides. You get x is equal to the cube root of 1, which is just 1. Right? So that's our second limit of integration. Now we have a full integral problem that we're able to do. So let's just go about doing this quickly. We already know the integral of this guy. subtracted from the integral of this guy, all from 0 to 1. That's since we both have x's and there's 0, we can just cross that 0 out. You can just do 2 over 3 subtracted to 1 over 3, which is 1 over 3. So that's how you would, that's the amount of area in between here. So what I did is that I plotted the function so I know which one's on top. Took my integral using the top curve minus the bottom curve. Found the intersection points by setting them equal to each other, okay? And just erasing this. So I'm going to give you a problem right now. And this is really going to teach you that the area between the two curves is the top curve subtracted by the bottom curve. Let's look at this example right here. Y equals arcsine sine theta, or y equals arcsine sine sine theta. And you guys are all good trig students, so you already know arcsine of sine is just canceling out, so you have y equals sine theta. Ha, I tricked you. So you want to find the area in between all of these curves, and let's say it's from 0 to 2 pi, okay? But be careful, we're not finding this, that, and that, and adding it. No. We're only doing the area in between. So the area in between would consist of this, not that, but this, and this. That's just a quick visual so that you just don't go out integrating everything that you see and then hoping for right answer, because you fail the AP test. So let's just look at this quickly. If we're going to write our integral problem based on what we just learned, we can't really do this simply, because from 0 to this intersection point, cosine is on top. And then from that intersection point to the next, sine is on top. And then we go back to cosine from that to 2 pi. So we're going to have 3 different integrals to write. And since let's find our limits of integration. And since we're all cool trig students, we already know when sine is equal to cosine. Pi over 4, 5 pi. So our theta would be 5, oh, nope, I lied. Pi over 4 and 5 pi over 4. So pi over 4, 5 pi over 4. Right? So let's start our integral. So to find the area, we take the area from 0 to the first intersection point of the top curve subtracted from the bottom curve in respects to x. But we also need this one too, so we're going to add it to get the summation of both of them. So we're going to add it to the area in between from where we left off to the next intersection point. Okay, from this, so we take our integral from the next intersection, from the first to the next of the top curve, which you can see is sine, subtracted from the bottom curve, which is cosine, and then in respects to x, and then you already know from the previous intersection point to the end point, it's going to be cosine, sine theta, in respects to x. So this is one huge integral that I am not going to solve because you guys can do it yourself, and I would not like to do this. But in the end, you should get something like 5.635 or something like that. But if there's anything that I am trying to pound into your head, it would be the area in between two curves is the top curve minus the bottom curve. Top curve minus the bottom curve. Top curve minus the bottom curve. And to find our limits of integration, you set the two functions that you're integrating equal to each other. Okay? So that's it for the area in between two curves. Good luck on the AP test. Please don't let me down.
Save a calculus kid, Jerry!
Saving your calculus grade, one function at a time.